Advanced Math, Lesson 47, Vertical Sinusoid Translations and Arctangent. So, again, quick recap, sinusoids, wave-like functions. Ones we're going to be focusing on in trigonometry are sine, cosine, and tangent. Not tangent, but sine and cosine. And we already learned about how to adjust the height or the wavelength of a sinusoid. And I believe, did we talk about learning how to shift them left and right? Can't remember. But we're going to learn about shifting them up and down right now. I don't believe we have left and right shifts yet. We'll get to that eventually. If you remember correctly, to increase the wavelength of a sinusoid, or to increase the size of the sinusoid's wavelength, we just have to multiply the sinusoid by the distance away from the center that we want it to be. So I realized I've been out of focus this whole time. So to recap, our base sinusoid will use the function of sine, which passes through 0 at an upward slope and follows that trend. And we've got breaks at 90, 180, 270, 360. Or in radians, we have pi over 2, pi, 2 pi over 3. Yeah. No, 3 pi over 2. Whoops. Had that one backwards. And 2 pi. I'll do this next piece in pencil. So to recap the size of the wavelength, if we wanted to just do +1, -1 on our wavelength, this would be the graph of y equals sine of x. Again, distance away from 0 being 1. Now, if we wanted to make this 7, let's make it +7, -7, this would be y equals 7 sine of x. Again, we're multiplying sine by the distance away from 0. If you look at the total height of the wavelength, this is actually 14. But what we're multiplying by is the distance away from 0. So, now let's talk about vertical and lower shifts. If you remember, to make adjustments away from the y-axis, all we have to do is add or subtract our adjustment with no sign change away from the x term. So if we bring this back to just y equals 1 sine of x, and we're not doing a distance of 7 from 0, this is just 1 and this is 1, -1. If we wanted to shift it down 3, what I do is I just take sine of x minus 3, or the other way to write it would be y equals -3 plus sine of x. So this would be, why am I going back to pencil? I remember why I never used pencil in the original videos. It's because it's hard to see. I just have to keep changing these numbers. So if I wanted to shift it down -3, the values of these numbers would actually change a lot. So the center of the graph is what shifts down -3. So if the center shifts down -3 and the wavelength varies 1 off, from -3 down 1, this would actually be -4. And then from -3 up 1, this would actually be -2. So what we'll do is I'll show you a graph next, and we'll determine the equation of that graph based on this new knowledge that we have of sinusoids. So let's look at this one right here. First thing to notice, our wavelength passes through 0, so we know this is a sine function. If the wavelength was above or below 0, then we would know it was a cosine function. Since it passes through 0 positively, I know that this is a positive sine function. Now, what I need to look at is the center line. The center line is at +4. So I've got y is going to equal a positive sine of x but it's going to be raised 4. So I'm going to have 4 plus sine of x. And then next thing I look at is my distance from the center line. The distance from the center line actually is 2 and 2 in each direction. So this sine of x is going to be multiplied by 2. So that's the equation right there. So again, the information we need to look at, the center line, what that value is, and then the distance from the center line that the wavelength moves. And so then that'll help us. Also, sine of x passes through 0. Cosine of x is going to be above or below 0. Inverse equations. So that one was a positive sine of x because it had a positive slope. This one is going to be an inverse equation. So passes through 0, so I know it's a sine of x equation. However, it passes through 0 at a negative slope, so I know this is going to be a negative sine of x equation. Now, I look at the center line, which is negative 10. Might be a little hard to see on the camera, but this says negative 10. So I'm going to have y equals negative 10 minus sine of x. And then the last thing, I'm going to check my distance from the center line. Here, negative 10 to 4, so that's a distance of 4. And then negative 10 to negative 6, also a distance of 4. So this is going to be 10 minus 4 times x, or 4 times sine of x. So that's my equation right there. Y equals negative 10 minus 4 times sine of x. That gives me my wavelength equation. So that's vertical sinusoid translations, and then also the inflation and deflation of the wavelength. I think those are the wrong words, but you know, you understand what I'm saying. How are we doing on time? Yeah, not so bad. Okay, so before we go into arctangent, I'll go ahead and do these 2 cosine examples. So like I said before, cosine is above or below 0. And we see here that this one is above 0, so this means we're going to be having a positive cosine of x equation. Or I'm sorry, actually this says theta, so this would be a positive cosine of theta equation. Honestly, if you use x and theta interchangeably in your homework, I'm not going to mark you guys off for that. I understand. So this is going to be a positive cosine equation because, again, wavelength is off of 0 and it's above 0, so positive. I'm going to look at my center line, which is negative 8. So y is going to equal negative 8 being added to the cosine function, and then I have to get the size of my wavelength. From here, negative 8 to 11 is 3, and negative 8 to 5 is also 3, so my wavelength is going to be 3. So y equals negative 8 plus 3 cosine of theta. That's this equation. Once more over here, I have a wavelength off of 0, but it's below it, so this is going to be a negative cosine of theta, or cosine of x. I look at my center line, which is positive 7 this time, so y is going to equal 7 minus cosine of theta, and then I look at the size of the wavelength. From 5 to 7 is 2, from 7 to 9 is 2, so this is going to be 2 times cosine of theta. So it's that simple. It's really that simple. Hope this makes sense to you guys. If you have any questions about this, let me know on Moodle. And then we'll look at arctangent. Excuse me. Okay, so arctangent. If you can remember, arctangent, arccosine, arcsine are kind of like saying we need to find the angle that has this tangent, or the angle that has this sine, or the angle that has this cosine, etc. And so, you know, we've typically done things like this, where we find the sine of the arctangent, or the angle that has the tangent of 1 over root 3. If we look at 1 over root 3 on our unit circle reference guide, just for the sake of time, because this video is going a little bit long, 1 over root 3 is going to be, where is it? Here. Here. And it's because opposite being, or the sine over cosine being 1/2 over root 3 over 2 inverts to become 1 over root 3. And the 2's cancel. So the tangent of 1 over root 3 is going to be 30 degrees. So when we say arctangent of 1 over root 3, it's the angle that has the tangent of 1 over root 3, so that would be the 30-degree angle. So then what's the sine of the 30-degree angle? Go back to our reference sheet, 1/2. Okay, You can use reference triangles to figure this out. Now, the way these problems are going to change is we're going to have the arctangent of the tangent of 135 degrees. So instead of us giving reference triangle values, we're going to be given angle values. And this changes the problem just a little bit because we have to focus on a couple of rules that I haven't mentioned before because they don't come into play very often if you're only using right triangle identities. But if you're using angle identities, you absolutely need to know these rules. And the rules are that for arctangent, if you're finding an arctangent, you have to stick with these first two quadrants. You have to stay in, or not these first two, you have to stay in quadrant 1 and 4, or from negative 90 to positive 90. The same is true for arc sine. You have to stay between negative 90, positive 90. And then for arc cosine, you have to stay between 0 and positive 180. We'll probably go over that rule more when we get to arc cosine and arc sine as they deal with these types of problems where we're using degrees. But for right now, we're only on arctangent, and we're just going to remember we have to stay in the first and second quadrant. So, and that's what makes these problems deceptive. So here we have an example that says we need to find the arctangent of the tangent of 135 degrees. And the reason why this is deceptive is because arctangent means to find the angle that has the tangent of 135 degrees. So the tangent of 135 degrees is going to be negative 1. So the tangent is, it actually becomes root 2 over 2 over negative root 2 over 2. Same number, just equals negative 1. So at first look, you would say, okay, I need to find the angle that has the tangent of this angle. So you would say, okay, well then the answer is 135 degrees. It's kind of like a double negative. But that's where those rules come into play with the quadrants of us having to stay in these first two quadrants. The reason why those rules exist has to do a lot with inverses. And the easiest way for me to show it to you is with a unit circle. Or, well, not a unit circle, but a graph. So let's say we're working with the tangent of 135 degrees. We are in this second quadrant. And then arctangent also implies a bit of inverseness. And it has to do a little bit with, it's something similar to what we see with negative vectors. So the inverseness would kind of be like the opposite force or the opposite angle. So that would put us over here. And you can actually see that with the first example that we did for the sine and the arctan of 1 over root 3. More or less. But let's stay on track. So if we did the opposite angle of 135 degrees, we would be over here, which would actually put us at negative 45 degrees, or at, let's see here, what is this, positive 315 degrees. So, if we go back to our unit circle and then we look at this area at 315, we also have the same number, which would be positive and negative, which would also give us a tangent of negative 1. If we go to the numerator, it's going to be a positive 1. So if we stick to these two quadrants, here we also have a tangent of negative 1. Here we would have a tangent of positive 1, but again, this quadrant is off limits, and then this quadrant is off limits as well, so we can't use 135. So the reason why we kind of stick to these two quadrants is because it gives us an inverse, it kind of gives us an inverse answer to the problem. So the answer for the arctangent of the tangent of 135 is actually negative 45 degrees. Now, some of you are going to think, hey, can't I just draw these and then find the opposite angle every time? Maybe. Try it out. Let's see if it works. I don't know. I've never done an experiment like that. So let's see if it works. If you want to challenge that problem, go ahead and try to solve them this way. See if the answers are consistently right. And if they are, I think you might be onto something. All right. If you have any questions, let me know on Moodle, and I will see you in class.